Hi everybody, this is video lecture number 2, I guess, and we're going to start looking through that book that you received in class today. Your exam date is June 24th, so it's a little bit over a month away. And this booklet will cover these major concepts. So we're going to take 3 concepts a day for the next 4 nights so that you're ready for Friday's test. This sentence is extremely important. You cannot passively prepare for chemistry regents. You can't sit in class and think you're going to absorb enough information to do well on the test. There are no shortcuts. You have to study, 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 ask questions, analyze the problems that I give you in order to be successful for the exam. Topic 1 deals with the atom, and this is all important stuff. The modern model has evolved over a long period of time through the work of many scientists. The major scientists we have to look at is Dalton. He came up with the theory of atoms, that elements are made of atoms, that all the atoms of an element are the same. So gold is composed of gold atoms, and all gold atoms are exactly the same. Atoms combine to form compounds. The Rutherford model, he bombarded gold foil with alpha particles, showed that most of an atom was empty space with a small, dense, positive nucleus. All of that is important. The Bohr model shows electrons in orbits around the positively charged nucleus. And the wave mechanical model, instead of orbits, we have regions of probabilities where the electrons can be found called orbitals. All of those are questions that can be asked. So sodium is composed of sodium atoms. Sodium and chlorine combine chemically to form an ACl. Aluminum, if we were to draw a Bohr model, has 13 protons in the nucleus, 2 electrons in the first shell, 8 electrons in the second shell, and 3 electrons in the third shell. It has an electron configuration of 283 and an electron dot diagram with aluminum and 3 dots for the 3 valence electrons. Each atom is made of positively charged nucleus with negatively charged electrons orbiting. Protons and neutrons are found in the nucleus. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. All of that is important. If we are neutral, the number of protons equal the number of electrons. Each atom has its own distinct amount of energy. When the electrons are in the lowest state, it's called the ground state. When it absorbs energy and moves to a farther out shell, it is in the excited state. When the electron returns to a lower energy state, it gives off the energy it absorbed as light. And we use this to identify an element with a bright line spectrum. So if I give you 27 aluminum 13, aluminum 27, we should know it has 13 protons. The difference between the two is 14 neutrons. And then protons equal electrons if it's neutral. So it has 13 electrons. This is the mass number. Can you tell it's 305? This is the atomic number. But if I were to give you aluminum as a +3 ion, it would still have 13 protons. It would still have 14 neutrons. But now it only has 10 electrons. The ground state is an electron configuration like 282, whereas in excited state, an electron has absorbed energy and moved to a farther out shell, so it could be something like 273. When the electron returns to the lower energy state, it gives off light. If that light is seen through a spectroscope, we see a series of lines that show where possible energy levels are as the electron falls back down. And these are called a bright line spectrum. The outermost electrons are called valence electrons, which affect the chemical properties of an element. They fill a valence electron to become stable by having somehow 8 electrons in their outer shell, except for hydrogen and helium, which only needs 2. Atoms of the same element have the same number of protons, so aluminum will always have 13 protons. Isotopes, same atomic number, different atomic mass, or same number of protons, different number of neutrons. And the average mass, we've done problems where we've had to calculate those. So all of this is important. So for instance, if I have nitrogen with a Lewis dot structure of this, it really means its electron configuration is 2-5, because nitrogen has 7 protons and 7 electrons, but only 5 of those electrons are valence. Carbon 12 and carbon 14 are isotopes of each other because they have the same atomic number but different atomic mass. And to calculate atomic mass, we take percent abundance of one isotope times its mass plus a percent abundance of another isotope times its mass plus, and we do this for as many isotopes as there are. Although officially we change the percent sign to a decimal when we do the problem. So as we move on to topic 2, this will be the last one we do today. So just to get us warmed up. So we're only going to do 2 topics. Nuclear chemistry, we just covered recently. There's a little mistake here. It depends on the ratio of neutrons to protons for stability. All elements higher than number 83 are radioactive. You should remember table N. We can find the half-life of a substance, of an element, radioactive isotope. On that table, we should be able to write equations of decay from table N. There are 4 types of reactions we should know, these transmutations, because they can occur naturally or artificially. We should also understand fission and fusion. We should be able to write an equation and interpret. And absolutely, we should know that the energy for a nuclear reaction comes from the conversion of mass into energy, from matter into energy. So the 4 types of reactions, if we take carbon-14, it will give off a beta particle as it turns into nitrogen. This is natural transmutation because the radioactive particle is to the right of the arrow. Nitrogen can be bombarded with alpha particles and turned into oxygen-17 and a proton. This is artificial transmutation because the radioactive particle is left of the arrow. Uranium can be hit by a neutron and turned into krypton. Barium and more neutrons. This is fission. And we can take 2 light nuclei, combine them to form a heavier nucleus, and this is fusion. The energy released from a nuclear reaction is much greater than from a chemical reaction. Nuclear reactions have risk, which could include radiation poisoning and cancer. There's also the issue of long-term storage and disposal, and not to mention nuclear accidents. And we should know some of the uses of radioactive isotopes, which include being used in medicines, as tracers, radioactive dating. So really, we're supposed to know cobalt-60 is used for cancer treatment. And iodine-131 is used for the diagnosis and treatment of the thyroid. So we're at the 14-minute mark, so we're going to stop tonight. So we have 2 of the units done. Have a great night, and we shall see you tomorrow.